is going to be the second part of digital filters. So slideshow, you check the mic is on. Yeah, perfect. Okay, from current slide and duplicate display. Okay, so we've seen last week a digital filter represented by the impulse response h of n is nothing but some numbers. Could be negative, could be positive, decimal, integer, doesn't matter. So that's one way of representing the filter. Another way is representing it by a summation of pulses. So each coefficient has an index. So initially, if there are no values written, so by default, the first index is at 0, second index at 1, 2, 3, and okay, let's assume there's nothing there. So in here, another representation could be a summation of pulses shifted by the index values. So this one shifted by nothing. So it's delta of n. Okay, so this one square brackets plus 4 delta of n minus 1 plus 10 delta n minus 2 minus 2 delta of n minus 3. All right. So, and we've seen the Z transform. So represented by h of z equal summation from n equals 0 to a certain value n or infinity, h of n z to the power negative n. So today we're going to talk about more information, something related to the Z transform. So we want the frequency response of the filter. So h of omega. And omega here you realize is just 2 pi f over fs. And to find definitely the magnitude and the phase for that filter. So we'll talk about the frequency response. Classification methods in terms of frequency selection. So we have high pass, low pass, band stop, band pass. We'll talk about some simple filter designs and some examples about first and second order. Remember, the order of the filter is the maximum delay. So going back to this slide, this filter is third order because I have delay 3. All right, so the frequency response of a filter is defined as the discrete time Fourier transform DTFT. You don't have to worry about like the whole details about DTFT, but it is given by this expression, h of omega equals h n e to the power j omega n. And this one is kind of similar to the Z transform. If you want to express this one as e to the power negative j omega n as z to negative n. So we can say this one is a special case where z equals e to the power j omega. So basically the frequency response is the Z transform, but when I take substitute instead of z, I substitute e to the power j omega. So an easy way to do it, you can find the Z transform and then you do this substitution. All right, so that's the frequency response of this impulse response, h of omega. And I have this impulse response h of n. And it is equal, like frequency response or transfer function and frequency domain is the same thing, y of omega over x of omega. And each filter comes with two things, magnitude or amplitude and phase. So the filter h of omega could be represented in this manner, h of omega. So that's the amplitude, and this angle h omega. So this one is the angles or the phase of h omega. Okay, so the magnitude frequency response is described as the effect of filter on amplitude of an input signal of frequency, like of certain value of omega. Basically, the filter, something like this, for example. it is a filter, so any signal outside this range of frequencies will be cancelled, and only these values will be permitted. And this is a special filter, we call it bandpass filter. We'll talk about it later. So basically, the filter here will just have an effect on the signal by either selecting that part of the signal or removing that part of the signal based again on a certain value of frequency. Then we have this angle representation, that is the phase of the frequency response. So it describes the effect of the filter on the phase of the input signal of omega. Usually we don't do much analysis of phase. However, phase is usually related to delay. But let's not worry about the mathematics behind it. The most important part is the frequency selectivity of the filter, and that will be do with the amplitude. So the frequency response, as I mentioned before, it is related to the Z transform. If you substitute instead of Z, e to the power j omega. Now, when we deal with frequencies, we have the frequency given and you have the sampling frequency. So these are, that's what we call usually a normalized omega. Normalized because I'm dividing over the sampling frequency. Typical example, I'll give you a certain filter or a certain Z transform and ask you find the amplitude of that filter. And this one is given by this example here. So calculate the gain of the following system transfer function at f equal 10 kilohertz, given that the sampling frequency used is 20 kilohertz. So this one here is given in terms of Z transform. If I want to represent it in terms of impulse response, what will be the impulse response? H of n? Like this question could be given in terms of h of n and h of z. If this one, I want to represent it by h of n with deltas. So what will be the h of n here? So here I have -1, no shift, so negative delta of n plus, so coefficient is 1, delta of what? N minus 2 plus 0.5 delta n minus 3. Or I can represent it another representation of h of n, -1, 0, 1, 0.5. So all these pieces of information will provide like the same solution. This one? No, -2. -2 because h of n, h of z summation n equals 0 to n, h of n, z negative n. So the negative here is coming from the exponent, not from this one. Besides, if I have delta of n plus 2, it means that I'm relying on a future value. The system will not be causal. So this is very unusual actually to deal with like signals plus shift, because that means that plus number means shift to the left. By shifting to the left, I'll go to the negative region of time and axis. So the system will not be causal. You're looking for the value in the future. So that's the usual here. That means it's shifted to the right. That's a delay. All right. So let me copy the question and solve it on the whiteboard. Okay, pick tool. Copy. All right, so I have this question, and that's the typical kind of question you may face in the exam. The only changes I will do is either express this one as h of n, and definitely I will change the transfer function coefficients. All right, so we'll start by finding h of omega. Okay. H of omega equals h of z at z equal e to the power j omega. So I'll have -1 plus e to the power negative j omega by 2. So this one will lead to this coefficient plus 0.5 e to the power negative 3 j omega. Now recall that omega equal 2 pi f over fs. 2 pi times f, 10 kilohertz, over sampling frequency, fs, 20k. So 2k, 20k, so I'll have 2 here, 2 and 2 will cancel, so it's going to be a pi. So that's the value of omega in this example. All right, so let's substitute negative 1 plus e to the power negative j. Now, instead of omega, that is a pi here, plus 0.5 e to the power negative 3 j pi. Now recall from Euler identity, e to the power minus j alpha equals cosine alpha plus, or sorry, minus j sine alpha. So I'm dealing with, so I have 2 pi here, my bad. 2 pi and 3 pi. So when we have alpha equal 2 pi, so e to the power negative j 2 pi equals cosine 2 pi minus j sine 2 pi. Simply in the calculator, you can find that this expression will lead to the value of 1. Just in the calculator, you substitute the value. Don't forget to change the angle from degrees into radians because you're using pi. All right, so this one equal negative 1 plus 1. Now let's do this one here. E to the power minus 3 j pi. So that's 3 pi here. So I'll do it at 3 pi and a 3 pi. This one will be 0, and I believe this is going to be negative 1 with a 3 pi. Or e to the power negative j 3 pi cosine 3 pi minus j sine 3 pi. So this one will be 0, and it's going to be negative 1. So plus 0.5 times negative 1. Those will cancel each out. So the answer will be negative 0.5. Now to find the amplitude, pi over 2. 10, 20k, 20k. So cancel. Okay. So it was 10k, 20k. What left is 2. 2 and 2 cancel out. So it is a pi. All right. So this is the frequency h of omega at f equal 10k, 10 kilohertz. Now I want to find the amplitude. Amplitude so the amplitude of h omega is simply square root of real part of h omega squared plus imaginary part of h omega squared. Now the square is for the imaginary and for the real, not for h of omega. All right, so I don't have imaginary part, so it's going to be square root of negative 0.5 square, square root of 25, or basically it will work as an absolute value here. So the answer 0.5. An important thing, amplitude is always positive. Amplitude is just a number. It's a square root of a summation of 2 squares, so it is a positive number. Now, what about the phase? The phase angle of h of omega equals tan inverse imaginary over real of h omega. Tan inverse of 0 over 0.5. negative. What will be the value?
0 over negative 0.5.
What will be the phase? What will be the angle? 0 divides negative 0.5. Okay, what will be tan inverse of 0? 0. Right, what will be the tan inverse of 0 over negative 2.5? 0.5. La, you have to be careful. Okay, take it as a fact. All negative numbers, if it's a negative number on its own, it's 180 degrees. But let's think about it. How it's 180 degrees or pi. Remember, you've done polar coordinates, right? And you've done like imaginary real axis. All right, so I have, this is my real axis, and this is my imaginary axis. So I want to represent the number negative 0.5 in this axis. So it is plus 0j, so?
Yeah.
So there is nothing in the imaginary axis, so I'm at 0. Now negative 0.5, where do I go with it? So that's a 180 degrees. So now if you use it in the calculator, you will get tan inverse of 0, you'll get 0. Okay, so always like have engineering sense, whatever they call it. So don't blindly rely on the calculator. Just look at the numbers, do this traditional classical method. At least you know in which quadrant your angle is. Now this one here, I have a real number. There's no imaginary, so I'm expecting it's going to be in the x-axis. It's going to be either 0 or pi or multiples of pi. But due to the fact that my number is negative, I'm with 180 degrees shift. If it was a positive 0.5 plus 0j, that will be a 0. But my axis here is like I'm using a negative value, so it's 180 degrees. So the phase of h omega pi or 180 degrees. Okay, clear? Okay, let's go back to the slides. I believe the solution is already provided. Okay, so this one does the amplitude. I think the question itself asks for the amplitude. It does not ask for the phase, but yeah, it's good to know how to find the phase. Duplicate slash. Okay, so classification of filters. There are several ways to classify filters. First, based on the coefficients. If the number of coefficients is finite, that's what we call a finite impulse response. Like it has 5 coefficients, 10 coefficients, 100 coefficients. So that's what we call an FIR filter, finite impulse response. Finite impulse response, FIR filter. So the coefficients of h of n is something you can count. Usually they are not expressed by an expression. So the impulse response of the filter is of finite length. Now there is infinite impulse response. So in this case, the impulse response of the filter is of infinite length. Several ways could be given by a mathematical expression. Or usually the other way, the common way, you have a feedback. So you'll always, whatever value of y will rely on a past value of y. Like there is some feedback going on. So that's the infinite impulse response. We'll talk about it not this week, it's going to be the week after. This is going to be the topic of next week. Basically, what we have done so far is FIR filters. Like this one is an FIR filter. Why? I have a negative 1, 0, 1, 0.5. So that's finite number of elements. That's 4 elements. So that's a finite impulse response filter, FIR filter. All right, another classification based on the realization. So recursive filters. Recursive means that there is a loop. It's a feedback. So the current output y depends on past outputs y of n minus k, where k is a constant larger than 0. So there is a feedback from the output of the input. So that's one way of realizing filters, like you have feedback. Another one, a non-recursive filter. There are no need for any past values of y, just shifted versions of x or the input. So in this case, the current output does not rely on the outputs y of n minus k or past values of y. So in this case, there is no feedback from the output of the system. Again, that's just classification. That's one way of looking at filters, but the major classification is this one, based on the number of coefficients. Another classification based on their frequency response. If you select low frequency components to pass, that's a low pass filter, something like this. Here, omega c, that's the cutoff frequency. Now, I'm not sure if it's going to be 2 T's or 1 T. So cutoff, let's keep it 1 T, cutoff frequency. Now, cutoff frequency has several meanings. A low pass filter, it means that it is the frequency where if the frequency component is higher than the cutoff frequency, the frequency will be, or the function or the component will be 0. Like if you have any element larger than the cutoff frequency, like here, there is no output. Below the cutoff frequency, like you will have some response. And that's what we call an ideal low pass filter. Ideal, I have a unity gain, constant gain, and the transition at the cutoff frequency is sharp. Of course, that's not realizable. A function like this is important to have in real time. If you remember in signals and systems, if I want to transfer this into time domain, what will be the inverse Laplace or inverse transform of such filter? You have a rectangular function. What is the inverse? It is a sinc. If you remember, that's the sinc function. Now, what is the main issue of the sinc function? I have negative points in time. It's not causal. So that's why such filter cannot be realized in real life. But there are approximations. We will not worry about approximations or realization in real life. We'll just know that there is a low pass filter. Inshallah, in future, we'll do filter design using MATLAB. There's a tool called filter design tool. You just give it the parameters that you want to achieve, like you want 5th order, 10th order, 100th order, and specify the cutoff frequency, sampling frequency, and so on. So you just give it all the parameters that you want, and just by a click, it will design the filter for you. All right, another part of filters, we have the high pass filter. Another thing you have to know in the frequency domain, it's like you have duality. So whatever you have at the positive, you will have it at the negative. So this one here is a mirror image of that one. That doesn't mean that this one is like a different response of this one. Like this one also, some people represented by one-sided Fourier transform, something like this. So that's omega C1, omega C2. Like 2 cutoff frequencies here, or sorry, up to pi. That's the whole, for the whole range. That's what we call a low pass filter. High frequency components above the cutoff frequency will be passing. All what you need to know is just like these classifications: low pass, high pass. Now, what makes the high pass filter special? Let's say it ends at pi. One thing we did not discuss, the Z transform or the Fourier transform for discrete signals if it's periodic over 2 pi. That means this signal will repeat itself after 2 pi. So here I have that part, then shift another part. Here's the 2 pi, and you have another image there. But let's not worry about 2 pi or 1 pi. Just know that this one stops at negative pi, from negative omega c to negative pi, positive omega c to positive pi. Now, if this filter stops at a point less than pi, then I'm rejecting frequency components higher than this. And that's what will lead to a band pass filter, like in this one. See, this one is pretty much looks like a high pass filter. However, like it stops at omega 2, it does not stop at pi. So these components will be rejected. Those components will also be rejected, and these ones here. So that's what we call a band pass filter. A band stop is the complementary of the band pass. Whatever was rejected here will be accepted here, and whatever was accepted here will be rejected there. So that's what we call a band stop, or another name, a notch filter. All right. So that's it about classifications in terms of frequency response. So we have classification in terms of number of coefficients, classification based on realization, and classification based on frequency characteristics. Here are some examples. Usually filters, when we design filter, we have basically all these components, regardless of whether low pass, high pass, etc. At the passing region, we have deviations. You will never have a perfect flat filter. Perfect flat, again, it's hard to achieve. It's not possible to achieve. But you'll get something like this. You'll have some deviations around the unity value. So you have the deviations by a constant delta P. And that's what we call pass band deviation. Pass band. Basically, the passing region where the signal is selected, that's the deviation at that point. Similarly, we have a deviation at the stop band. So here is what we call a stop band deviation. Delta S. And this one here, we have a transition. Again, you will never have a sharp transition like the ones here. This one, again, impossible to realize. Okay, so you have that's delta P, that's the pass band cutoff frequency, that's the stop band frequency here. So that's the transition band. So this one, what will we say? That's the pass band, and this is the stop band. Now, if you want to design a filter, let's say want to have delta P very small. So I don't have much deviation in the pass band region. Similar thing at the stop band. I want it very small. And also the transition delta P minus delta S, omega P minus omega S, I want it also very small. And the closer to zero, the better. This could be achieved by having higher order filters. Later, inshallah, once we are done with the IIR, I'll show you the filter design tool, and we'll see that by changing the order of the filter, we will have better characteristics for the output filter I want. So 10th order versus 100 order. Yeah, the 100 order will achieve better characteristics. However, I need more memory because coefficients at the end of the day, they are numbers. They need to be stored in the computer. 10 coefficients and 100 coefficients. So that filter requires 10 times the memory when compared to that 10 coefficient filter. All right, so here are the key points. The edge frequency for the pass band, edge frequency for the stop band. Here the transition width, deviation, pass band, stop band deviation. Now there is a concept called the ripple. The ripple is related to these deviations here. Ripple is given by this expression, usually it's in dB, 20 log 1 plus delta P. Okay, and the same thing for the attenuation. We don't call it ripple, but it's the same kind of concept given by the same expression, but with a negative because it's an attenuation here. Because I'm attenuating the signal here. All right. Okay, so these are the characteristics of every filter you may design in the future. Some filter designs here. Basically, if you want to design a filter, you will look into certain characteristics. First, you look where the zeros are, where the poles are. Zeros will tell you where the magnitude will be 0 for the filter. And the poles for stability, that's for sure. The closer your pole to the unit circle, the higher frequency response you have. So place zeros at angular frequencies that you want to stop. So that's going to be associated with the stop band region. The poles at angular frequencies that you want to pass, the pass band region. Now, the closer the zero to the unit circle, the lower the correspondence magnitude frequency response. Opposite, the closer the pole to the unit circle, the higher the correspondence magnitude frequency response. So you cannot say, oh, I will design my zeros and I will get my desired response. So you have to monitor both actually, the zeros and the poles, because their effect is opposite to each other, so you have to maintain a balance between both. Definitely for stability, all poles must be inside the unit circle. So to ensure real valued filter coefficients, and that's something usually prefer to deal with, real valued coefficients, poles and zeros must either be real or must occur in complex conjugate form. Actually, this wouldn't happen, let's say, by default. All complex number we deal with, they are in the complex conjugate form. So some common filter designs we have, for example, that's the general expression of a low pass filter. You don't have to memorize it, but that's a low pass filter. So here the hint is place the pole at a low frequency at omega equals 0. So in this case, that's the low frequency component. And for stability, the value of R less than 1. So place the 0 at high frequency and you have these hints, and that's the impulse response of this filter. So for instance, is this one FIR or IIR? ولا IIR, infinite impulse response ولا finite impulse response? IIR. Why? I have a shifted version of Y because it's not limited. So you have Y of n equal X of n plus X of n minus 1 plus R of n minus 2. Let's say you have Y of 10, it will depend on Y of 9. Y of 20, so again, it represented expressed by a function. All right. So that's an example of low pass filter. If you want to see the response of this filter, it will be something like this. So here the value of R is 0.8. So that is the 0 of the function or the pole. Yeah, that's the pole here. So it is inside the unit circle. It is stable. That's the 0. It's at the unit circle. And that's the magnitude response. That's a low pass filter. So low frequency components are passing, high frequency components starts to increase. Now, in terms of quality, I would say that's a bad low pass filter, because up till the whole frequency range, like you still have some signals passing. Phase, again, usually it's hard to, let's say, find a proper meaning for phase when compared to the magnitude, but that's the phase response of the filter. Notice also the magnitude is usually expressed in dB and decibels. All right. Another filter here, that's a notch filter or a band stop filter. So second order notch filter with the notch at omega naught has 2 poles at the origin and 2 complex. That's the expression. Let's see the response here. So I have the poles here, 2 poles at the origin, and I have the zeros there. So band stop filter. So it will stop, like it kind of consider this the stopped region if I want to draw it in ideal filter representation. So that's the band stop filter. Again, this one is representing only the positive half of the frequency response. Like, where is it? This one, that's a band stop filter. So I'm representing in the graph there in MATLAB, I'm showing only this half. So notice there that we have this spike, that is 0. And I have these responses. So if I want to consider this one area A, area B, area C, if I want to go back there, that's my area A, that's my area B, that's my area C. So that's a band stop filter. I'm stopping the region of, let's say, from 0.2 to 0.3. That's the normalized frequency. We'll talk about it later, inshallah, when we go deep into MATLAB. Okay, then we have digital resonator here. It's a second order with a resonance frequency of omega naught. Digital resonator is a recursive IR linear system, have a complex conjugate pair of poles. And let's see the response of the resonator. That's a band pass filter, I believe. Something like this. So this is what's passing, assuming, and everything else will be rejected. Now, be aware that these are in decibels and 100 decibel, 20. So these are high values, actually. Even if you are, let's say, getting here 20 decibels, 20 decibels is a good value, actually. It's not very small. So that's a band pass filter. We've seen this one before. If you want to realize a filter using a block diagram. So here, is gain. You multiply by a -1. Here's the time shift. And for example, you have this filter x of n minus x of n minus 1. So I have x of n. You give it a delay. So I have x of minus 1, n minus 1. I have the negative sign here. And you have x of n. You don't have to multiply by 1. It's like this one, this gain expression is not necessary. So you get it there, and that's it. That's your adder. That's the summation point. And that's a simple filter with two coefficients. If I want to represent this filter here, it's going to be delta of n minus delta of n minus 1. Simply because you will convolve x with delta x of n, convolve delta of n, you'll get x of n. And the other part, x of n, convolve with delta of n minus 1, you'll get x of n. Just one point here, discrete, so we'll have to write it using square brackets. And then the z transfer function, etc. All right, so that's a simple filter design using the block diagram. Another filter here, there is no need for future values of, past values of y. So that's a second order filter. I have two delays. We've seen that actually last week, so nothing new here. And that's it. It's quite a short lecture. Kind of complement what we did last week. The only concept here is filter design and gains. Like these values, how to find the gain, how to find the phase. Yeah, that's it for this lecture. Let's have a break because we have a meeting at 1. And after the break at 1:20, 1:30, we'll come back to do the tutorial session. Okay. All right. Let's go there.
At 1:20 or 1:30 though?
1:30. Stop recording. I'll upload it later, inshallah, into Moodle. So I have this question. So provide the transfer function below. Calculate the gain of the filter at the following cases or frequencies using the frequency response given that the sampling frequency 44 kilohertz. So that is Fs given as 44K. So as we did before, H of omega equal 1.25 plus 0.5 e to the power minus j omega minus 0.1 e to the power minus j2 omega. Now omega is 2 pi f over fs. So h of f. Now initially we used to call it omega, but since I convert everything in terms of f, I'll call it h of f. 1.25, 0.5 e to the power minus j 2 pi f. I'm going to put 44K because it's a constant, minus 0.1 e to the power minus j. So I have 2, and there's another 2 that's going to be 4 pi f over 44K. All right, so the question is find the response of the filter at these values of frequencies. So the first one is quite easy, 0 hertz. Then I have 11 kilohertz, 22 kilohertz. So h of 0, just substitute 0 and you'll get 1.25 plus 0.5 times e to the power 0 basically because I have f equals 0 minus 0.1 e to the power 0. So you have 1.25 plus 0.5 minus 0.1 and you will get 1.65. And there is no unit. This is the gain. All right. So the other case, 11 kilohertz. So H 11K, that equal 1.25 plus 0.5 e to the power minus j 2 pi 11K over 44K minus 0.1 e to the power minus j 4 pi 11K over 44K. So let's do some simplification. Plus, so I have 2 times 11, that's 22 over 44, so that's going to be 1 over 2. So negative 0.5 is for negative j, k and k will go 11, 2, so I'll have 2 here, so it's going to be pi over 2 minus 0.1 e to power. So 44, 4 times 11, that's a 44, and 44 they will cancel, so it's going to be negative j pi alone. All right, so let's do it here on the side. E to the power negative j pi over 2 equal cosine pi over 2 minus j sine pi over 2. So you'll get cosine of pi over 2 is 0 minus j sine pi over 2. That's going to be 1. So this whole thing will lead to a negative j. Okay, so this one here, I'll substitute it later as negative j. The other one, e to the power negative j pi equal cosine pi minus j sine pi. All right, cosine of pi is negative 1 minus j sine of pi, that's going to be a 0, so it's going to be negative 1. So this whole thing is a negative 1. So let's substitute that in the expression. I will get 1.25 plus, I have minus, oops, minus 0.5 j plus 0.5. So, because I have negative 1 by, sorry, 0.1. So it's going to be 1.35 minus 0.5 j. Then the amplitude of h of 11k equals square root of 1.35 squared plus 0.5 squared. Can you do that in calculator? That's going to be 1.44. All right, so last part will be at 22 kilohertz. Okay, oops. So h of 22k equal 1.25 plus 0.5 e to the power minus 2 pi j 2 pi 22k over 44k minus 0.1 e to the power minus j 4 pi 22k over 44k, so 0.1. All right, so let's see if we can simplify. So I will get 1.25 plus 0.5 times e to the power minus. So that's going to be 2 by 22, that's 44. Okay, so it's going to be minus j pi minus 0.1 minus j, I believe it's going to be 2 pi, so. Okay, I think e to the power negative j pi, we already found out that it's 1. Now e to the power minus j 2 pi equals cosine of 2 pi minus j sine pi. That's a negative 1, sorry. Well, 1, negative 1. So I will have cosine of 2 pi, that's a 0, minus, sorry, cosine of 2 pi, that's 1, minus 0, that's 1. And this one is negative 1. I have a negative 1 here. Okay, so I will get 1.25 plus 0.5 times -1. أيوة. Negative 0.1 times 1. 1.25 minus 0.5 minus 0.1. So it's going to be 0.65, I believe. 0.65. Now, if I want the other part of the question, we're done. That's the first part. So all those, we found them. Now draw the graph of the gain and determine what type of filter this is. So if I want to express this one in terms of points, so this is F. Okay. Something going on. I'm losing the cursor. Okay. That's F and H of F. And by the way, this one, the gain will be 0.65. I'll have to do the calculation for that. So at 0, at 11K, at 22K. So at 0, what was the gain? 1.65, I believe. 1.65. At 11K, 1.44. At 22K, 0.65. Now, in this case, what do you guys think the behavior of this one? If I want to draw it, so this is the frequency, and this is H of F. So that's a 0. That's 11K. That's 22K. So at 0, I have the highest point, 1.65. At 11K, 1.44. Something like this. 0.65, something like this. You can tell it's what? So low frequencies pass, high frequencies rejected. So that's a low pass filter. So, okay, where do you need any assistance? Okay, you're fine up to this table, right? Now we want to find the behavior of this filter. Is it low pass, high pass? Now we see that with the increase of frequency, so as 0, 11 kilohertz, 22 kilohertz, the response is becoming smaller. So the higher the frequency, the lower the response. So that's a low pass filter. So if we want to pass any signal, this part will be passing. And after, let's say you can set like this. So at high frequencies, I have a low gain. That's a low pass filter. So this is a characteristic of a low pass filter. You see the solution. Okay, so 1.65, that's the first one, 1.44, the second one, 1.65, and there goes something like this. So that's a low pass filter. Quite straightforward. Okay, last question. Provide the transfer function below. Answer the following associated question. What is the frequency response H of F? And calculate the gain of this filter at 3 kilohertz, given the sampling frequency is 8 kilohertz. All right, it sounds easy. Probably it is easy, but let's see the math behind it. Copy. All right, so let's find H of omega first. It's asking for H of F. Okay, let's do H of omega first. It's going to be 1 minus 5 e to the power minus j omega plus 4 e to the power minus j 2 omega over 1 minus 2 e to the power minus j omega. But I want H of F. 1 minus 5 e to the power minus j 2 pi f over fs plus 4 e to the power minus j 4 pi f over fs. 4 pi because I have 2 pi here, and omega equals 2 pi over f over fs, so 2 pi, and the 2 here, that's a 4 pi here. Divides 1 minus e to the power minus j 2 pi f over fs. So it's pretty straightforward. Okay, let's confirm to avoid surprises later. There it goes, just the same thing. Now this is the part that I have substitute for f3 and fs8. So at f equal 3k, fs equal 8k. Let's see what will be the behavior of this system. 1 minus 5 e to the power minus j 2 pi times 3 over 8. I will not put the k, they will cancel each out, plus 4 e to the power minus j 4 pi times 3 over 8. 1 minus e to the power minus j 2 pi 3 over 8. Okay. So let's do it with Euler. Simplify, so 3 and 3, so that's 3 pi over 4. 4, 2, that's 3 pi over 2. 2, 4, 3 pi over 4. So let's do e to the power minus j 3 pi over 4 cosine 3 pi over 4 minus j sine 3 pi over 4. What is cosine 3 pi over 4? Square root of 3 over 2. Okay, so it's negative 0.707. Okay, so negative 0.707 minus j, same thing. So should be the same. Okay, now e to the power minus j 3 pi over 2 cosine 3 pi over 2 minus j sine 3 pi over 2. So it's going to be j. This one will cancel because that's a power, like a multiple of pi over 2. And this one, 3 pi over 2, the sign is going to be negative 1. By negative is going to be positive j. All right, so I have all the information needed. So let's substitute the values. So we will have 1 minus 5, 0.707, negative 0.707 minus j 707 plus 4j over 1 minus the power, that's 3 pi over 4, which is this one. So that's 707 minus j. Okay, so the question is asking for the gain, right? Calculate the gain. So let's simplify the upper one. 1 minus plus 5 times 7. So 3.5 and 85. Check. 5 times 707. 3.5. 3. Okay. Five, 3, 5 minus same thing. 3 point minus by minus is going to be plus 3.535, and we have a j plus 4j. 1 minus is going to be 1.707 plus J 0.707. Okay, so let's see, just look at the original function. Okay, so there is a 2 that I did not add, so there is a 2 here. That's why it's always good to check. So there is a 2 there. And there is a 2 here. So this one will be different. So this one is 1.414, 2.414 plus 1.414J, صح? Double check. Because there is a factor 2 here, if we forgot to multiply with. Okay. Okay, so this one is gonna be 4.35. 1 plus 535. I just added these two numbers plus J7 0.535 divide 2.414 plus J 1.41. All right. Are we done? No, we need to find again. How to find again for this? How you divide two complex number? Multiply by the conjugate. How to multiply by the conjugate? Of the denominator. So we multiply by 2.414 minus J 1.414. All right, let's see what we will get. So multiply this by this. Calculator. It's going to be 10 something. Okay. 10.95. Yeah, let's take only 2 decimal points. Then this number by this number. Then let's multiply this number by this number. 18.19. Okay, so let's look at the sign. So I have a negative. J by J, that's a negative, so it's going to be plus. Multiply those. 10.65. J times J. So negative 1. By negative, say plus. All right, what about those two? As simple. Square this one and add it to the square of this one. Because you multiply by the conjugate, so the complex parts will cancel each other. So 2.414 squared plus 1.414. 7.82. That's the whole thing. All right, that equals. So let's get the real parts together. So I'll have 21.56, 21.6, صح? Okay, so I have negative plus J 18 minus 6, 11 0.66 divides 7.82, and that equal. So distribute the division. 21 divides by 7. What? 49. Now the amplitude of H of 3 kilohertz, square root of 2.76 squared plus 1.49 squared, 3.13. Okay, so let's see how it was solved there. Okay, complex, and there we go. 3.14, 3.13 is no big deal. Yeah, 2.176, 1.5, and we did it 1.49, so it's the same. You want to find the phase shift tan inverse? Okay, if there is a question, tan inverse of 1.49 over 2.76. How much? Two. Change to degrees. هلا you can 28.36 degrees أو 0.495. Both are the same, but you have to specify radian or degree. Yeah, like when you put the angle, you put the unit, if it's radian or degree. طيب. So where does this angle first, second quadrant, which quadrant? First quadrant. Okay, take it as, I will not say as a rule, but when you look at these numbers, so let's say like this, that's the real, and this is the imaginary. And this is going to be the quadrant. If both of them are positive, that's the first quadrant. Okay. If the real one is positive and the imaginary one is negative, which quadrant? Fourth quadrant. هيك باخدينها؟ Advanced math أكيد. Advanced math. If this one is negative and this one is positive, second quadrant. If this one is negative and negative, third quadrant. No, I never actually taught it or learned it this way. It comes with experience. So that's why when you have the angle 0 over -1, like the example we did before, so this is the real part and this is the imaginary part. The imaginary part is the negative. So it's going to be either this or this. But it will not like be in any quadrant, so it will be in the middle. 0 is no, there's no sign. So it was in the second half. It was in the, like the x-axis at the negative side. Alrighty. So yeah, that's it for today. Pretty straightforward. Yes. هلا you may and you may not. لأنه what if you did something wrong? How I'm gonna give you credit or partial credit at least. And then in the exam you'll have plenty of time, so there's no need to worry. But you always like keep the calculator to confirm, to assist, but letting it to do the job might mislead you. All right, so that's it. Stop recording.